drive this session with an immense pleasure, I introduce and welcome our next speaker, Dr. KP Navin. He is an assistant professor, Electrical Engineering Department in IIT Tirupati since July 2017. Before joining IIT Tirupati, he was with the Department of Electrical Engineering, IIT Madras, as a DST-inspired faculty. He obtained his PhD degree from Department of Electrical Communication Engineering from IISc Bangalore. Subsequently, he worked as a postdoctoral fellow at INRIA, France. He also worked at the ISRO Satellite Center, Bangalore, as Scientist C. His research interests include statistical modeling and performance analysis of wireless networks, network economics, game theory, and optimal control. I cordially request Dr. KP Navin to take this forward.
Thanks, Vamshi, for the cordial introduction. Right. So, I will dive into the basics of probability. So, I am not assuming any kind of prerequisites here. So, this can be a standalone session here. So, it's used in versatile places actually, probability theory. Right. So, even in machine learning. So, later we will see how we will use techniques from probability theory when we talk about reinforcement learning. Okay, so this is going to be the outline. So, I'll start with the basics of probability. Okay, I'll start from the very basics, and then later we'll go into talk about random variables and expectations. Right. So, many of these terms at undergraduate level you will already be familiar with. We will formally go into each of these topics, and depending on the the availability of time, we'll look at some advanced topics. So, particularly concentration inequalities and law of large numbers. So, these like relate fairly advanced. So, perhaps we will not have time to get into this, but we will see how it unwinds. Okay. Right. So, when it comes to probability, right. So, everyone has, or at least will make some probabilistic statements. Right. So, suppose some cricket match is going on. So, we will always say that okay, with some probability this team is going to win and so on. Right. So, somewhere we know about probability. Right. So, let us start with very simple examples, right. So, for instance, like rolling a dice. Okay. So, now here is two scenarios, right. So, if you are allowed to bet, what would you bet on, right. So, outcome is 1, right, or outcome is even. So, there are two possibilities, where will you place your money on, right. So, what would you bet on? Outcome is even, right. So, even without explaining much, you intuitively know something about probability, right. So, why would you choose event B? Because chance of occurrence of B is greater, right. Although we have not formally defined what it is, but it already makes some sense to you, right. Now, here is another possibility, outcome is even, outcome is odd. Okay. So, what would you bet on now, right. So, where will you put your money? Yeah, right, because it does not matter, both have same chance, right. So, now this word chance, it means something, right. So, we know what it is, but we have to formally define what exactly we mean by chance. Okay. So, probability theory is exactly about that, right. So, it is a mathematical approach of formalizing our intuition about chance of occurrence of certain events. Okay. So, we are talking about chance, but what exactly it is. So, how to model these events or these scenarios. Okay. So, that is going to be that is about probability theory. Okay. So, that is the entire study of probability theory is on that, right. So, applications are several actually. So, I come from wireless communication and networks domain. So, if you talk about bit error probability, so you are interested in what is the chance that these many bits are going to be in error, right. So, if there are more bits in error, so you lose a packet at the receiver end, right. So, you have to formulate such events, and also, so this simple. So, and also probability is used in more involved scenarios, right. So, you have always been using Wi-Fi, but you know a lot of random events occur in Wi-Fi, right. So, suppose several users try to access the Wi-Fi access point, there is collision, right. So, how to avoid collision? They have to make probabilistic decisions at the Wi-Fi access point. Okay. So, probability finds natural applications in such scenarios. So, in electronic circuits as well, right. So, when you are fabricating large number of chips, so you have to decide, so what is the fraction of chips that are going to be in error, right. So, you should try to minimize that fraction, as much as possible, right? So several areas like I have mentioned here, right? Even in reservation systems, if you take your flight reservation or hotel reservation, so the general procedure is they'll generally overbook, okay? Overbook than what is the available number of seats. The reason is they'll take a chance there. So they, based on previous experience, past experience, they will predict that some number of customers are going to cancel their reservation, okay? So that's, so everywhere there is some kind of risk and reward involved, okay? So so there are many domains where you will find the natural application of probability theory. And I'll just start with like lot of references. So many standard books are there, newer books are coming. So this is on basic probability theory. So my personal favorites are this book. These are authors from MIT, Bertsekas and Sitsiklis. So introduction to probability, and also this is a very classical book, Robert Ashe on basic probability theory. They are also on advanced topics. So there are a lot of books on random processes and so on. Okay, now even before we begin the study of probability, so we should first understand, right? So there is something called as an experiment, okay? You conduct an experiment and then you will start asking questions, okay? So you have to first describe an experiment. What is the experiment that you have in mind or you are planning to conduct, okay? So experiment could be as simple as tossing a coin or rolling a dice, right? Outcomes are very simple. Or it could be as complicated or as transmitting a known signal over a wireless channel, right? So you do a transmission, so it's not received exactly at the receiver end, right? So there is so much of noise gets added to the transmission. So so your experiment could be as complicated as that, okay? So now so what we will do is we will introduce this notion known as probability space, right? Where we will try to capture the essential features of our experiment, okay? So what is this probability space? So there are two components. So one is it has two components, sample space. The other thing is known as the probability function. In advanced probability you will come across a third component called as the sigma algebra, but we will not worry about this at this stage, okay? It's not necessary. We will just, so there is a sample space and there is a probability function, right? So now these things will become clear once we start looking at some examples. So what is sample space? See, you conduct an experiment, so many outcomes are possible, right? So if you can list out all these outcomes, so that's your sample space, okay? It is the set of all possible outcomes of an experiment. Let's start with very simple examples. You are tossing a coin, so this is your sample space, right? Head or tail, as simple as that, okay? So if you are let's say tossing a coin twice, right? So what is your sample space now? Yeah, exactly, right? So it's all pairs of outcomes, okay? The four possibility now, okay? Tossing a coin, now here is will slightly make it interesting. Tossing a coin until an head appears, okay? So what is your sample space? All possible outcomes. So you are tossing a coin, you will wait until an head appears, okay? Exactly, okay? So it's like this. So head, right? So head could appear in the first toss and tail and head, right? So you see, now here it was like I could say that there are two outcomes, there are four outcomes. So here, right? So it is countably many outcomes, right? So there is a possibility that you can see 1 million tail followed by an head. There is some small probability of that, right? We should not discard such events also, although the probability of that is very low, right? So this for this particular experiment, so this is the sample space, right? Now again, so rolling a die, so now it's again fairly straightforward. So there are 6 possible outcomes. Now you can mix and match all these different experiments and call it as one single experiment, right? So my experiment is tossing a coin and rolling a die, okay? So that's my experiment, right? So once you are very clear about this notion of experiment, you should be able to write down a sample space or at least specify a sample space for you to work on or address questions related to probability, okay? So here it's again head and the outcome of the die, okay? Then tail and outcome of the die. So there are 12 possible outcomes here, right? Okay, now, so these are all finite and countably many, so the sample space contains so many elements or so many possible outcomes or possibilities, okay. Now here is one simple experiment. So what I will say is, so it's like I call this as the one dimension dart game. So you know dart, right? So you take a arrow and then put it on the board, right? So I am just imagining a one dimension version of it, right? Or think of it like picking a point on a line. So there is a line 0, 1. I will ask you to randomly pick a point from that line, okay. So here the sample space is, it could be any of the point, right. So here it is uncountable now, okay. So there are many, so infinitely many outcomes here, okay. Okay. Now tossing a coin infinitely many number of times, although abstract, but I am just thinking about these examples, right. So where will such outcomes, you might ask a question, where would I come across a scenario where I will toss infinitely many coins, okay. Now think of a communication scenario. So tossing a coin, think of head as bit 1 and tail as bit 0, right, and suppose you are transmitting a video file, it is made up of millions of bits, zeros and ones. It is a sequence of zeros and ones. Suppose you start transmitting that, you do not want, so certain times moving to an infinite sample space will help us, okay, in dealing with questions related to probability. Okay. So now, so the next, so once we are clear about our experiment and we have identified a sample space, so the next task is we have to understand what are known as events, okay. Right. So these are essentially subsets of sample space. So these are known as events, right. For instance, if you are tossing a coin, one event could be so this is an event. So this is the event that head occurs, okay. This is the event that tail occurs, okay. Now in the example of tossing a coin twice, so this is your sample space. So this is my event. So sometimes I will mention events in statements, okay. So A is at least one head occurs, okay. So what is this set now? At least one head occurs. Out of these 4 outcomes, which are favorable or which falls in this category that at least one head has occurred, okay. See here, so this and this, right. So at least one head occurs, okay. So you can now you can just create as many events as you want. See, exactly one head occurs, okay. So this is another event, okay, exactly one head occurs, right. Now yeah, so few more examples here. So suppose I am rolling a die, outcome is even, outcome is odd. Now you told that in the initial example, I asked what would you bet on, right. So you told both are equal, right. Now you see both have equal number of elements or the equal number of outcomes in both sets, okay. So it does not matter which set you pick, but still we will have to formalize this notion, okay. Now here one dimensional dart game. So if I ask you the question, distance to the midpoint is less than 0.1, okay. So you have a one dimensional setting. So I am saying that distance to the midpoint is less than 0.1, okay. So in this particular example, so what is your set A, okay. So you had, so this is your sample space, okay. So 0 to 1, okay, and this is your midpoint, okay, 0.5. So distance to the midpoint is less than 0.1, okay. So essentially this interval here, right. So 0.4, 0.6, okay. So all points here, right. So this is your set A, okay. So A is this interval is less than 0.1, right. So 0.4 to 0.6, okay. So I hope you understand this notation, right. So this is a open bracket. So that means 0.4 and 0.6 are not included, okay. Yeah, so I think they're less than or equal to, or yeah, so you can just correct that. So distance to an end point is less than 0.2, okay. So you can think about this. So end point is less than 0.2, right. So now here are, so once, so now, so we are dealing, we have come into the set theory area. So right, so let's understand some properties of sets. Okay, so essentially there are only three important set operations, right? Rest all can be derived from this. Okay, it's a combination of these set operations. Okay, so one is union, intersection, and complement. Okay, so union is A union B is like all elements that are either in A or B. So very elementary, right? So these are so intersection of two sets. So only those elements that are both in A and B, and complement is those elements that are not in A. Okay, so any other set can be expressed as set of these operations. Any other complicated operation is essentially a combination of these three. Okay, so now a few more definitions here. So you take two events A and B. So they are said to be disjoint if this holds, right? So they are disjoint sets, right? If there is no element in common between both of them. Okay, and here is one more definition here. So they are said to form a partition if this holds. Okay, so A intersection B is they should be null set, and if I put both together, okay, it should be yes. Okay, I think this is A union B. Okay, the mistake here. So A union B should be the entire sample space. Okay, and this is the familiar De Morgan's law. So I will not go through this, but the way you prove equations of this form is you take an if I ask you to formally prove this statement, so what would you do is you take an element here and show that that element is here, right? So then you take an element from here and argue that that element belongs to this set. Right? So that's the way to prove equalities related to set. Okay, so then so we talked about this now sample space and events inside the sample space. Now the key component, another key component is we have to talk about probabilities, right? We have to start assigning probabilities to these events now, right? Now, so okay, so what is this probability function that we are talking about? So essentially it should assign real numbers to events, okay, and it should satisfy certain certain properties. Okay, so what are those? So your chance should be a number between 0 and 1, right? So we'll truncate it to 0 and 1. Okay, it's a number in 0 and 1. So probability are essentially 0.1, 0.5 or so on, right? Some number between 0 and 1. And probability that, see, if you conduct an experiment, one of the outcomes should occur. Okay, so that means, so the probability of the entire sample space is 1. Okay, so definitely that event is going to occur, right? And if two sets are disjoint, and so then probability of A union B should be P of A times plus P of B. Okay, so these are known as the axioms of probability, right? So so any function that satisfies these three properties are referred to as the probability function. Okay, if you can come up with a function like that or assign a function that satisfies these three properties, so they are known as, it's known as a probability function. Okay. Right. Okay, so now again let's go back to these examples. So if you take this example of tossing a coin, see, you can simply assign, see, this is an outcome. So probability of head is 0.5, probability of tail is 0.5. Okay, so such a coin is known as the unbiased coin. Okay, so unbiased coin. So you can also bias the coin. Bias in sense, I can say that probability of head is 0.75, probability of tail is 0.25. Okay, so I am just assigning probability. So now before even you can ask questions about certain events, you should have first assigned these probabilities, right? For your experiment, a priori you should have assigned these probabilities and then start working addressing or start addressing questions related to probability. Okay. Now, so in general, so what you can do, so we have something known as the Bernoulli probability function, which says that probability of head is P and probability of tail is, naturally it should be 1 minus P, right? Because if you add up both, it should sum to 1, right? So the total probability should be conserved. Now, so in the case of rolling a dice, so here is one example of a probability function. right? So I'll assign equal probabilities 1 by 6. Of course, you can bias it, okay? So you can say probability of 1 is more than 1 by 6. So then somewhere the probability should reduce of one of the other outcomes. Right. So once I assign these probabilities, now you can start addressing these questions, right? So if I ask what is probability of A, right? So the way to look at it is like this. The P of A is probability of this set, right? And but this set is made up of 3 different sets, right? So individual sets which are disjoint 2, 4 and 6. Now you just add up those probabilities, okay? Now, so again this one dimensional example, I have to assign some probability, right? I will say that probability of any interval is simply the length of that interval, okay? So there is some abstractness involved here, but we will just stick to that definition of probability. Simply length of the interval is probability of that particular event, right? So now here what are the probabilities? What is P of A here? Distance to the midpoint is less than 0.1, right? Simply the length of this interval, which happens to be 0.2, okay? So if so distance to an end point is less than 0.2, 0.4, right? So any of the end points. So there are 2 end points here, 0 and 1. So there is an interval of length 0.2 here, another interval of length 0.2 there, okay? So it's 0.4, right? So again, so you can work out, so probability of A union B, A intersection B and so on. Okay. Now, so I'll just quickly go into some more properties of probability, okay. So rather straightforward, so it's very easy to prove. Just for completeness I am mentioning it here. So if you have if you have an event, so P of A plus probability of its complement should be 1, okay. So if you have the null set and the entire sample space, so that probability should be 1 because 1 is the complement of other, and the probability of null set is simply 0, right. So this we are able to show from the axioms. We did not assume this, but just assuming the axioms we are able to show that, okay. Then monotonicity property, okay, if one is subset of other, so P of A should be less than equal to P of B. So this is the famous union bound. Maybe you have come across this, or maybe many would have remembered this, okay, union bound, okay, P of A union B, right. So you can actually formally prove this, okay. So I will leave it as just an exercise. You can go back and see how you can prove this just using the axioms of probability, okay. And okay, so this is just a general union bound, right. So now see, one of the very key component of probability is to understand or gain intuition for this notion of conditional probability, okay. So we always condition on certain events, because once you are conducting experiment, maybe in between you get some information. So based on that information you should readjust the values of probability, right. So these days if you are any cricket match or any competitive game, even in tennis, so you will see if you are following, you will see that chance of winning, right. So initially maybe if both teams are equally good, it will be 0.5, both they give 50% chance. As the match progresses, you will see that the chance keeps varying, okay, because given that an event has occurred, they will start re-evaluating the values of these probabilities, okay. So they are always conditioning on events that have already occurred, okay. So that's about conditional probability, okay. So I'll formally define. So see, the conditional probability of an event B given event A, that means event A has already occurred. Now what is the chance that event B has occurred or would occur, okay. So it's something like that. So P of B given A, okay, it's defined like this. So P of B given A, probability of A intersection B divided by P of A. So let's look at some examples here. Now suppose you are rolling a dice, right. So there are 6 possible outcomes. So I am saying that probability of each outcome is 1 by 6. And now, so I will take this event A, right. So A is the event that outcome is even, okay. So that's probability is half. Then B is the event that the outcome is 2. So probability is 1 by 6. Now what is P of B given that A? So if I tell you that, so I've just conducted the experiment, means I've rolled the dice. I'll only give you the information that the outcome is even, okay. So it could be your outcome or it could be any of the other two outcomes, right. So now what happens to the probability now? P of B given that A has occurred, right. So if I tell you that A has already occurred, you can definitely say that the other outcome has not occurred, right. 1, 3 and 5 are ruled out, right. Now this becomes your new sample space. So there are 3 elements in this sample space, one is your favorable outcome, okay. So your probability is 1 by 3, it has increased now, okay. So the chance of your event has increased. So earlier it was 1 by 6 before I conducted the experiment, or without any side information it was 1 by 6. Now once I feed information, right, your probability has increased, okay. So conditioning, so it's not always true probability will increase, right. I'll give examples also. So conditioning can sometimes increase the probability of an event. So there could be other examples also, right. So here look at this example here. So A is still the same event, outcome is even, and now here is another event C, I will call it as C, outcome is less than equal to 3, okay. So probability of C is half. Now what is probability of C given A? So given that A has already occurred, right, 2, 4, 6, right. So how many is favorable for you now, okay. So 1 by 3, right, 1, only this event, now these are ruled out, 1 and 3 are ruled out, only there is one favorable event, right, out of 3. So originally your probability of C was half, the probability has reduced now, okay. So conditioning can sometimes decrease the probability of an event, that can also occur, okay. And now there are some special scenarios where conditioning can leave the probability unaltered, okay. So here is a scenario like that. So this is my event A. So I am defining event D as the event that outcome is less than equal to 2. Okay. So the original probability is 1 by 3, but once you condition, still it remains as 1 by 3. Okay. So there is one now. So here there are 2 outcomes out of 6, but once I tell you that event A has occurred, so one of the outcome is ruled out, but still there is one outcome out of 3. Okay. So earlier it was 2 by 6, so now it is 1 by 3. Okay. So sometimes, so conditioning can leave the probability unaltered, and now this special case is known as independence. Okay. We will say that these 2 events A and D are independent. Okay. So we will talk about that in a while. Okay. So let's look at some properties of conditional probability now. So we have this something known as the chain rule. Okay, so this just follows from the definition itself. So I have defined probability of B given A as a P of A intersection B divided by P of A, right. So it follows from that definition, but it can be generalized now to more than 2 events. Okay. Then so you have something known as the first base rule. So essentially I am reiterating, sorry, I am just iteratively using the definition of conditional probability. Okay. So P of B given A is P of A intersection B, right, but I am writing that as P of B times P of A given B, right. So divide by P of A. So this is something very important. So theorem of total probability. Okay. Now if you have an event A, and if you know that these events is going to form a partition of the entire sample space, okay, and these are disjoint events, right. So then you can write it in this form and start using the definition of conditional probability. Okay. So there are some, if you see, base rule is something very important, right. So even in case of GATE exam or something, there will be standard question on base rule. So once you know about conditional probability, it's very easy to address those problems. Okay. And this is something known as the second base formula. Okay. Right. So we have been just staring at some equations. So I have been recapping a few things. So let's see now. Let's try to apply these things to some simple problems. Okay. So very simple setup here. So let's see how we can use make use of base rule to solve some problems. Okay. So I'll just first choose this problem, okay. So I'm going to call it as the hat problem. So here is the setup. So let's say there are like n people in the room. So let's say everyone is wearing a hat, right? And now what you will do is you will just run. So you can think of it as coupons also, from some random coupons also. Or you will just throw the hats into a bin, and now you will randomly choose one, okay. Now the question is, what is the probability that you will get your hat, okay. So that's the question. What is the probability that you will get your hat, okay. Now the experiment is not well defined, okay, still not well defined. So I have to give you some more information. So here, so if you are the first one to choose, okay, so what is the probability that you will get your hat, okay. So any guesses? Okay, yeah, so you can be more confident. Yeah, 1 by n, right. So naturally you will think it is 1 by n, right, because there are n hats and there is one that belongs to you, so randomly you are picking, right. So it's 1 by n, right. So one possibility out of the n various possibilities. Now I'll slightly increase the complexity. So I'll ask you, oh, okay, so I think, yeah, so 1 by n, right, yeah. So I'll slightly increase the complexity now. So here is the question. So if you are the second one to choose, okay, so there is already before you there is someone choosing the hat, right, and you are the second one to choose, right. So what is the probability that you will get your hat? 1 by n minus 1, so n into n minus 1. Okay, so many versions are there. So let's see. So that's the part with probability, right. So to some extent it will be intuitive. So but to derive at the right answer, so we have to make use of the machinery that we have discussed so far. Okay. So in general, I can ask you the question: what if you are the kth one to choose, or what if you are the last person to choose? Okay. So you get the last person, so only one hat is remaining. What is the probability that that will be your hat? Okay. Huh?
You are the last person is if you are not.
No, before you others have chosen, right. So let's say there are random coupons, so forget about the hat, right. So let's say random coupons, so you will go, everyone has picked coupon. Let's say they have not revealed what is there. Now you are the last one, right. So let's say roll numbers are given to everyone, okay. So you will go and pick, right. So what is the probability that you will get your coupon, okay, coupon with your roll number? Okay. So let's see now. So let's see what is the answer in this particular scenario. It's a simple question, but let's try to. So now, so intuition is not going to lead us too far here, right. So we have to slightly work out some details to understand what could be the solution, right. So here, so let's just derive the solution formally, okay. So if you are the second one to choose, okay, so I'll define two events here, okay. So first event is, so you get your hat, that's an event, so that's a possibility, right, you can get your hat. I defined that as event A, okay, although I have not talked about what is the experiment and sample space, so there is some experiment, some sample space, right, we can write it down, but at this stage I will just use words here, okay. So A is you get your hat, so B is the event that first user gets your hat. I have defined two events, okay. Now you see the power of Bayes rule. So my interest is, I am asking this question, P of A, probability that you get your hat, okay. I have just used Bayes rule here, okay. P of B, P of A given B plus P, so this is the total probability theorem, P of B complement, P of A given B complement, right. Just work out the details. See, P of B, first user gets your hat. Once the first user has got your hat, there's zero probability you will get back your hat. It's over, okay. So this probability is 0. Now, first user has not got your, so what is B complement? First user has not got your hat. What is the probability of that? You should pick anything other than mine. So out of n hats, there are n minus 1 other hats. He has to pick one of those. And then what is the probability that I will get my hat? 1 by n minus 1, only n minus 1 hats are remaining. You see, 1 by n, right. So the probability remains unaltered. Even if I go and pick second, probability will remain unaltered. So this is something counterintuitive. It's not very straightforward. So unless you formally note it down, okay, so you will not so you cannot guess this answer, okay. So similarly, if you are the kth one to choose, we can just generalize now, okay. So A is the event that you get your hat. So then I will define this event. Bi is the ith person gets your hat, right. So let's say you are the k could be anything 2, 3, 4 or so on. Maybe you are the 5th user. You will go and just pick your hat. Try to pick your hat, or you pick a random hat. There is possibility that you get your hat, or the ith person might have already got your hat, okay. So then again you can apply total probability theorem. There will be so many terms. Once one of the users, one of the other person, right, has got your hat, probability that you will get your hat is 0, okay. Now this is the only possibility now, right. See, I have applied iterative chain rule now, okay. So probability that the first user does not get my hat, so out of the n hats, you should not pick mine. So n minus 1 other hats he has to pick, okay. Then the second person comes, so n minus hats remaining, you should not pick my hat, so n minus 2, right. So again you do all these things, right. So it's a telescoping product, so the terms will get cancelled, okay. And finally 1 by n will remain, this 1 and this n will remain, again it's 1 by n, okay. So that's very interesting, this will hold for any k. So that means even if you are the last person, let's say there are 1000 people, there are 1000 coupons, right, and then they say that okay, you go and pick, if you get your coupon, you are lucky and we will give you a reward, right. Now people will be in a hurry to go first, right. So now it says that it doesn't matter, okay, there is no need to hurry up, okay, you can wait as long as you want, whatever is your term, probability that you will get your coupon is 1 by n, it remains as it is, okay. So these are some very interesting problems, okay. So more you can find actually, but you will be able to solve once you formalize these things, okay. You cannot intuitively guess that these are going to be the probabilities, right. So for some simple setup you will be able to guess, otherwise you have to work out the details, okay. It's always safer to work out the details before making a guess, okay. Now, so let's look at one more problem, okay. Here see, I just ignored this notion of sample space and so on, right, but there are some scenarios where you have to construct a sample space, otherwise you will not be able to address the questions, okay. Yeah, okay, so again, yeah, so this was the thing, right. So I'll just complete this part now. So we know the answer, okay. Now I'll again, so if I change the setup itself, I'll say okay, everyone will choose simultaneously, okay, everyone is randomly at the same time given your coupon, okay, given one of the coupons, okay, is assigned, one of the coupon is assigned. What do you think will be the answer now? What is the probability that you will get back your coupon or your hat? Okay. So now your notion of experiment has changed now. Earlier people were going one by one, right? Now the notion of experiment has changed. Okay. So it's you have to think, your sample space has changed now, right? So what was the sample space in this particular example? One of the hats, right? So you are the first one, you will go and choose the hat. You don't worry what happened after you choose an hat, right? So if you are the second one to choose, so you will be concerned about what happened before you choose the hat, right? So here the sample space is pair of hats or pair of coupons, right? So what do you think is the sample space here, and what could be this answer? Okay. So think about this. So you can try to make a guess, but and also verify whether your guess is correct by formalizing things. Okay. Right. So I will not fill this gap here. So you can work about. You can start thinking about this question. Okay. Now I will take one more example here. Okay. So this is a very popular game show. There was a popular game show based on this. Okay. Now I call this as the 3 doors problem. So let's say there are 3 doors, and there is reward behind one of the doors. Okay. So there is some. Let's say I am constructing this game. I put reward somewhere in one of the doors. Okay, so you do not know, it's hidden actually. Okay, now I'll ask you to choose a door. Okay, you can choose one of the doors. Okay, 1, 2 or 3, right? And now once you choose a door, I'm going to eliminate one of the door. Okay, because I'm setting up this game, I know which door has reward and which doesn't have reward. I'll eliminate one of the door which doesn't have a reward. Okay, so only one door has a reward. So once, let's say you choose one, there are 2 more doors, so I'll eliminate one of them. Okay, now only 2 doors are left now, your initial choice and one other door which I have not eliminated. Okay, now the question is, I'll ask you whether you will still stick to your initial choice or you want to switch to the different door. Okay, so you want to win the reward, so what would you do? What do you think is best to do? I've removed 1, 2 are left. Okay, right, what do you think is best to do? You will stick to your initial choice or switch? What is better? You can take a guess. Okay, looks like 50-50 chance, right? There are 2 doors and reward could be in one of them, right? So it doesn't matter whether you stick or switch to your, or you stick to your choice or you switch to the different door. Okay, so now sometimes what will happen is when we scale up things, no, intuition can help. Okay, so let's slightly scale up things now. So let's say there are 100 doors. Okay, and now I'll ask you to pick one of the door. Okay, the reward in one of the just one door alone. Okay, so there is reward. So there are 100 doors now. You go and pick one. Okay, so you'll pick one. So what I will do is I will eliminate 98 of them. Okay, because I know where I place the reward. I'll eliminate other 98 which doesn't have the reward. What would you do now? Would you stick or would you switch? Okay, right. So let's see now. So let's see if how to work out problems of this nature. Okay, so here no conditional probability or anything, but here the thing is you have to now carefully think about what is the experiment and what is the sample space, and then you will be able to address decision problems of this nature. Okay, so I will say that this is my experiment. So what I have done is I have just simplified. I will say that since I am setting up the game, I know that okay, reward, let's say, is hidden under door 1. It's arbitrary. Okay, not randomly. I am going to go and place it. I have just chosen door 1 just for simplicity. It could be any of the door. Okay, you can pick it. Okay, now what you do is you are going to randomly choose a door. Okay, and now so reward is here. You might choose this, or randomly you are going to choose. You might choose one of the door. Suppose you happen to choose this. I have to eliminate one other door, right? Let's say I am going to eliminate this door. Okay, that's for simplicity. Okay, maybe a priori I have thought. Again, I can, all these things can be, so I have just made the experiment simple. I could make it complicate also. What I could do is I can pick even before you choose a door, I can randomly pick a door and place the reward. Okay, that's just going to increase my sample space, but the basic final probability will remain unaltered. Okay, so let's see. So what is the sample space here? So I'll call this as the sample space. So it's all possibilities. Okay, the door that you are going to select and what remains actually after eliminating the door. Okay, so there are only 3 possibilities. So you can pick door 1. Okay, then I'm going to eliminate 3 and door 2 will remain. Okay, or you can pick door 2. I cannot eliminate this because reward is hidden there. I should not eliminate this. Okay, otherwise you will not receive any reward. Okay, that's unfair. So what I will do is I am going to eliminate this. Okay, then only 2 and 1 will remain. Or you could pick this. So in which case I have to eliminate door 2. Okay, only 1 will remain. 3, 1. Okay, so now let's see, with this sample space, let's start addressing certain questions now. So let's assign the probabilities. So since I am constructing the game, I'll assume that you randomly are going to pick one of the doors, right? So 1 by 3, there are 3 doors, randomly you can pick one of them. So what happens? So winning probability under no switch. Suppose you don't switch your door, and out of 3 outcomes, when do you win? Only when you pick door 1. Door 1 and you stick to that door, you say that no, I don't switch, then you are going to win. The probability is there is 1 out of 3 outcomes, 1 by 3 is the probability. So now you have decided to switch. When would that happen? That would happen if you have chosen if you have either chosen door 2 or door 3, and after elimination you decide to switch, right? There are two possibilities. So if you decide to switch, there are 2 favorable outcomes that can help you win the reward. Okay, so 2 by 3. Right? Now you see there is a higher probability of winning if you switch the initial choice. Okay, so it says that okay, switching is better. It seems like switching is better, but always these statements you should take it in a probabilistic sense. Okay, these are all random quantities, right? So maybe you think that switching is better, but there is a chance that this event has occurred and you switch and you lose. Okay, these are all probabilistic statements only. Okay, nothing in random, so nothing can be told with guarantee. Okay, essentially like share market. So there is always a chance that you will lose, and so one has to be very careful about this probabilistic statement. Okay. Right. So these are some 2 simple examples about how you can apply techniques from probability to answer some questions. Okay. Now, so let me proceed further now. So after conditional probability, so another important concept is known as independence. Okay. So here is the formal definition. So events A and B are said to be independent if this occurs. Okay. So P of A intersection B is P of A times P of B. Okay. So essentially, given that A has occurred, probability of B should remain unaltered. Okay. So an event has occurred, that's not going to affect the event that I am interested in. So then I can say that A and B are independent. Okay. So here is a couple of examples. So if you are going to toss a coin twice, so this is your sample space. So then probability of an outcome is 1 by, so there are 4 outcomes, so 1 by 4. So this event A, first toss is head, second toss is head. Okay. So these are going to be independent, right? So first toss, the outcome of the first toss is not going to affect the outcome of the second toss, right? So, but formally let's work it out. Okay. So you have to verify essentially this formula. What is probability of A intersection B? Both should be head. Okay. That is essentially 1 by 4, which is actually P of A times P of B. P of A is half, P of B is half, so 1 by 4. Okay. So now you can say that A and B are independent. So now, so here is another example. Okay, so here tossing a coin twice. Now here is my event A. Okay, so at least one head. Okay, let's say at least one head. So the event is this one, right? Out of, so these are the 3 favorable events. At least one head has occurred here. So at least one tail, right? So these are the events. So now if I ask the question, what is the probability of B given A? Okay, so it is going to be 2 by 3. Okay, but originally probability of B was 3 by 4, right? So now A and B are not independent. Okay, so this is how you will argue whether 2 sets are independent or not. Okay. Now, one mistake generally many students do is to think that disjoint events are independent. If 2 events are disjoint, to think that they are independent is not correct. Okay, disjoint events are not independent, right? So here is one example, right? So the event is both heads. This is the event both tail occur, right? These 2 are not independent, right? Because if this event occurs, for sure this event would not have occurred. It cannot occur. Okay, if this event has occurred, this cannot occur, right? So the way to do is you just verify P of this should be intersection here. P of A intersection B, essentially null set, but P of A and P of B had positive probabilities. Okay, so the condition for independence doesn't hold, right? So whenever you want to check whether 2 events are independent, you have to essentially verify these conditions. Right. So now, so you can go ahead and generalize this notion of independence to more than 2 events. Okay, so if you have 3 events, you can say that they are said to be mutually independent if these condition holds, right. So, what are there are three events now, it's not just this condition alone, okay. So, all these things should hold. So, they are pairwise, they should be independent, okay. If only these condition alone holds, we just call them as pairwise independence, okay. So, there are examples we can give where they are pairwise independent, but not mutually independent, okay. And if they are mutually independent, they should be pairwise independent, okay, because this condition should naturally hold. Okay. So, then now, so we will gradually now go into this notion of sub experiments also, right. So, many times what you will do is essentially while simulation or something, so you will reconduct the experiment many times, okay. So, once you conduct an experiment, you will get a value, again you will repeat the experiment, you may get a different value and so on, right. So, this generally happens when you are simulating certain events. So, then we need to understand this notion of sub experiment, okay. So, what you will do is you will keep repeating the experiment several times. Now, those are the original experiment I am calling it as sub experiment, and a collection of those sub experiments I am calling it as the experiment now, okay. So, for instance, tossing a coin twice, tossing a coin n times, you could roll a dice twice, rolling a pair of dice, okay. So, the same experiment is conducted 2 times or multiple times, okay. So, now sub experiments are said to be independent if events related to different trials are independent, okay. Now, here in the case of tossing a coin twice, the trials are independent with, let us say, probability of head in each trail remains as p, right. So, every time you toss, probability of head is p, right. Now, you can start computing different events, right. So, what is the probability of this event now, head and tail? The way to do it is like this. So, you have to take event A, head has occurred here, and see the first head in first trail, okay. The second could be anything. Now, this is another event, tail in the second attempt, okay. So, here it is tail, the first event could be anything, right, head or tail. Now, I can this particular probability that I want, p of h comma t, I can express it as p of a intersection b, okay. So, and now since I am claiming that these are independent experiments, you can write it as p of a into p of b, p times 1 minus p, okay. So, of course, you knew that it is p times 1 minus p, but this is a formal way of approaching that intuition, okay, right. So, now again now we will start talking about different probability functions. Suppose you are going to toss a coin 5 times, okay, and I say that these trails are independent with p being the probability of head, right. So, if I say what is the probability of this sequence to occur, you will just see, look at number of heads, number of tails, right. So, p square times 1 minus p cube, okay. So, and now this is also similar. So, even this sequence has the same probability, right. So, there are 2 heads, 3 tail. So, this is going to be this probability again, okay. So, now if I ask the question, what is the probability that there are going to be exactly 2 heads, right. So, out of 5 possibilities, 2 heads should occur, right. It could be in any of the position. All those sequences will have same probability, like here p square times 1 minus p cube, right. So, that is going to be the probability of all those sequences. You have to just count how many sequences are there, right. So, it is like 5 choose 2, okay. Out of 5 positions, you have to choose 2 positions, okay. So, this is 5C2, if you are not familiar with this notation, but this is the scientific notation for 5C2, okay. Then probability, right. So, these many sequences are there, okay. So, if you just add up, the probability of all those sequences is same, right. So, it is going to be this one. Now, why only 5 times? You can toss the coin n times. So, then you have the binomial probability function, okay. So, this is a very popular probability function. You would have used it in many scenarios, okay. Probability of exactly k heads is something like this, n choose k, p power k, probability of head is p, right, 1 minus p power n minus k. Now, again tossing a coin until an head appears, right? So this, if you remember one of the initial experiment, right? I keep tossing until an head appears. So each of these trails are independent, okay? So probability of head is P. Now this is so P of H. So if I am lucky, so I'll see the head in the first toss. So it's simply going to be the P. P of T comma H, right? So 1 minus P times P, 1 minus P square times P, and so on, okay? Now what you have is this one now. So it's known as the geometric probability function, okay? Probability of first head in the kth trial is 1 minus P power k minus 1. The first k minus 1 trials, I should see a tail followed by an head, okay? So that is P, right? So now that we have started introducing these different probability functions, so I think we are ready to discuss about random variables and expectation. I'll take a small pause here. So if there are any queries related to this part, so I'll be happy to address. Okay. So anything related to, or if you know the solution to the modified version of the hat problem or something, you can guess here. Okay. Right. Okay. So otherwise, so we'll just we'll proceed here. So now, so we have been talking about these probability functions, right? So now let's go into some more details now. Okay. Now, what is a random variable, right? So I've been talking about head, tail, right? Tossing a coin 2 times, right? But if you want to do some scientific experiment and make some reasonable analysis, you have to assign numbers to certain quantities, right? So eventually, end of the day, you are interested in knowing results in the form of graph, or some numbers should be, something should be quantified, okay? So random variable is essentially used for that purpose, okay? So what is random variable? A random variable is a real valued function on the sample space, okay? So let's look at examples. So if you are going to toss a coin, these are the 2 outcomes, head and tail, but these are symbolic outcomes. So I have to assign numbers to these, okay? So this is my random variable. So x of h is 1, and if the outcome is tail, so I will say that this random variable takes value 0, okay? Now tossing a coin twice, you can define a variety of random variables. So based on the kind of questions you want to address, okay? So I will call x as number of heads in the outcome, okay? So this is my random variable, right? So now what is the value this random variable takes for each outcome? So it just counts the number of heads in the outcome, okay? So here it is 2, for these 2 it is 1, for this outcome it is going to be 0, okay? Now here is another random variable. So I am going to define it in this form. So I will define y as, it takes only 2 values, 1 or 0. It takes value 1 if first toss is equal to second toss, otherwise it will take 0, okay? So on the same experiment, on the same sample space, I have defined a variety, I can define a variety of random variables, okay? So only if for this outcome and this outcome, this random variable is going to take value 1. For the other 2 outcomes, it's going to take value 0, okay? So there are many possibilities here. But one thing to understand about, yeah, let's look at one more example and I'll make that statement in a while. Now you are going to toss a coin 10 times. The sample space is set of all these head tail sequences. You can think, so I'm just asking, so how many sequences are possible, okay? So, right, so head tail sequences, so how many are possible? Okay, so you can think about that. Huge number of sequences are possible here, okay? All head tail sequences. Now, so what is, so I'm defining my random variable like this, okay? So number of heads in the outcome, right? Essentially you just count how many heads are there, okay? So for this particular outcome, it is 6, okay? Here is one more random variable. Here is an interesting example now. So it will make you think. So number of times h is immediately followed by a tail, okay? See, I have defined a involved or complicated random variable. Yeah, No, I didn't give the outcome also. So you guessed it. So yeah, but oh, you were guessing for this one. I think you are guessing for this sequence, right? Number of times H is immediately followed by a tail. Okay, head is immediately followed by a tail. How many are there here? H, head, tail, head, tail, head, tail. 3. Good. So here, oh yeah, same. It's essentially same sequence I am giving. Okay, 3. Okay, right. So that's the thing. So we can define complicated versions. So it's about how or what is the objective from the experiment or what we are trying to analyze. So we can define a variety of random variables, right? In some instances, this random variable will be useful. For some other analysis, some other random variable may be useful, right? But one key point about random variables is there is nothing random about random variables. That's something you have to understand. Okay, so only the term says random variable, so there is nothing random about it, right? So once you have defined your random variable, for every outcome, for sure you can assign some number. Okay, there is always some confusion that random variable is some random quantity. No, it's a fancy name for a function. It's like any other function. F of x is, let's say f of x is x square, right? So given any x, you will tell what is the value of f of x, right? So similarly, once you have defined your function for any outcome, this is like your x, this is like your f of x is some 6. Okay, all the randomness lies in your probability function. Okay, not in the random variable. Random variable is well defined, deterministic. So there is no confusion about, no randomness in random variable. Okay, so that's something you should understand. Right, so let me go through a few more concepts which you already may be familiar with. So one is something known as the CDF, okay, cumulative distribution function. So this is the definition. So CDF of a random variable is defined like this. So this is the standard notation for CDF. So just be careful with the notation. All random variables will use generally capital values, and small values are real numbers. Okay, so fx of x is probability x less than equal to x. And now what is this event? So this is the probability is for events, not for random variables, right? Now what is p of x less than equal to x? We have to understand that. That is set of all outcomes such that x of s is less than equal to, it should be x here. Okay, x. So right, so this p is a function that is assigned to events. Okay, so now this is also an event. What is this event? This is essentially will collect all those outcomes for which the value of the random variable is less than equal to x. So that's what it does. So this is an x here. So this is a typo here. Okay, so just be careful. Okay, right. Let's say p and 1 minus p is the probability. P is the probability of head. 1 minus p is the probability of tail. And now if I so I have defined this random variable x like this, 1 and 0, right? Head is 1, tail is 0. Now compute this one, fx of 0.5, right? So just go by the definition. Okay, so always in mathematics, so try to go by the definition and see what leads to the other. Okay, so then finally the value. Okay, probability that x is less than equal to 0.5, right? What outcome will attach you, will this statement leads to, right? When is x less than equal to 0.5? When the outcome tail has occurred, right? So this is essentially like asking what is the probability of this outcome occurring, right? So that is 1 minus p. Okay, fx of minus 1. So I can plug in any real number. Okay, I can plug in any real number. So fx of minus 1. What is the probability that x is less than equal to minus 1? Okay, so you have to ask the question, what outcomes will yield a value of x being less than equal to minus 1? No value, right? Head is 1, tail is 0. No outcome can give you a value of x less than equal to minus 1. So essentially, it's probability of empty set, which is 0. Okay, fx of 2, right? X is less than equal to 2. It could be either head or tail, right? So that probability is going to be 1. Now what you can do is, so with this you can sketch the CDF of this particular random variable. Okay. So, you see I am varying x here, and this is the CDF for values of 0, values of x less than equal to 0, it is going to be 0, and now at 0 you see there is a jump of 1 minus p, right, and there is a reason why I put this dot here, right, because at 0 the value is 1 minus p, we saw that, okay, fx of 0 is 1 minus p, and then again it is going to stay constant here, and again at value 1 it is going to jump to the height of the jump is p, the total probability is going to be 1, right. So, this is CDF of this random variable. Now, you can think of this as an exercise. Suppose you are going to roll a dice, what is the CDF? So, there are going to be 6 steps there, 1, 2, 3, 4, 5, 6. Okay. First, yeah, so that is the rolling dice. Also, you should define what is the random variable that you are thinking about. Okay. Here. So, because on that particular experiment I can design many random variables. Okay. So, for the trivial random variable which assigns value 1 to the outcome 1, value 2 to outcome 2, there will be 6 jumps. Okay. Height of each jump is going to be 1 by 6. Now, this is something you should know about CDF. So, the first two are relatively straightforward. It says that it is non-decreasing, right. As you increase the value of x, your CDF should always be increasing. Okay. Suppose somewhere you come across an interview and then they show you some function and ask you whether this is a CDF. Okay. So, you should be confidently able to tell whether it is or it is not. Okay. It should be an increasing function, CDF. Okay. And CDF is essentially evaluating probabilities, right. So, it should be numbers between 0 and 1. As your value of x increases, it should approach 1. For negative values of x, it should go to 0. Okay. Because in one direction, probability of x, when x is very large, essentially like probability of the entire sample space. Okay. It will start collecting more and more outcomes. Once you start reducing the value of x, outcomes keep coming out of the desired set, you will keep approaching the null set. Okay. And the third point is technical. It says that fx is always right continuous. Right continuous in sense, whenever there is a jump, you will see that these dots always will be towards the right side. Okay. So, that is one more key property of a CDF. Okay. So, the jumps, it is continuous from the right. So, if you approach the CDF from the right hand side, it should be continuous. Okay. Now, so let us look at a few examples. Okay. So, discrete and continuous random variables. So, a random variable is discrete if it takes only finite or countably infinite values. Okay. So, essentially if the CDF, if you see that the CDF is piecewise continuous or piecewise constant, so such random variables are known as discrete random variables. Okay. So, here this example, right. So, this what we had is a discrete random variable. So, in such scenarios it is convenient to work with PDF. So, this is another concept that you have you would have heard, probability mass function. Okay. So, PMF, PDF is for the continuous version. So, probability mass function, right. So, it essentially just goes at those points where the breaks are there, you just find out what is the probability or what is the mass of the probability at those points. Okay. So, you will get a stem graph like this. So, now let us look at some common discrete random variables. The simplest one is this Bernoulli random variable, which we have been talking about. So, this is the notation for the Bernoulli random variable. Okay. So, Bernoulli P, and then so this is the PMF of the Bernoulli random variable, and so the tossing a coin, transmitting a bit, right, wherever there are two possibilities, so we always come across Bernoulli random variable. Okay. The very simplest form of random variable. Okay. Now, this is I talked about geometric random variable, right. So, here is the representation. Okay. So, this is geometric P. So, it is a single parameter random variable, we call it as just one parameter is enough to know the PDF about this random variable or PMF. Okay. So, PMF is like this. I talked about the geometric distribution, right. So it's essentially the PMF of this is the PMF of the geometric random variable, and the example is tossing a coin until an head appears. Okay, and this is the PMF of a geometric random variable. So it's very easy to sketch these PMFs, right? You can change the values. So they are very simple commands in MATLAB, okay, to sketch the probability mass functions of some very popular random variables. You can just play around with P and see how the distribution varies. Okay, so very easy to do that. So then we have the binomial random variable, and this is the form of this is the PMF of a binomial random variable. And now binomial random variable is a 2-parameter random variable. It has n, which is number of times you conduct the experiment, and p is probability of success during each trial. Okay, so n times you repeat the same experiment n times, p is the probability. It's like n different Bernoulli random variables. Okay, so that is binomial. Okay, so example is like tossing a coin independently n times. Okay, x is the number of heads in the outcome. Okay, so then one more very important discrete random variable is this Poisson random variable. Okay, so this is the notation. Okay, so x is Poisson lambda, and see, suddenly we are talking about discrete random variable. All these has some very good examples, right? So a lot of intuition was there. Suddenly it looks very alien actually. So this is the PMF of a Poisson random variable, Px of k. So some lambda power k by k factorial e power minus lambda. Okay, so suddenly we do not know what is the example for this. It looks like something a strange random variable, right? For others we had very simple and very nice examples, tossing a coin n times and so on. Okay, now so Poisson random variable is very useful. Actually it is a good approximation for binomial random variable. Okay, sometimes when you conduct an experiment, your n may be very large. Okay, n may be of the order of 1000 or 10,000 or so on. Okay, then this Poisson random variable is a good approximation for binomial. When this happens, right, as your n increases, let's say the success probability, you are going to scale it as lambda by n, right? So then this is a result actually. If xn is binomial, then under the limit as n becomes very large, the PMF of this random variable converges to the Poisson random variable. Okay, so let's look at that. Okay, so this is the PMF of the Poisson random variable. This is the PMF of Bernoulli random variable when n is equal to 10, right? I am stopping at 10 here, right? I am just increasing, right? So I am going from 10 to 11, okay, 11 to 12, right, 12 to 13. You see how quickly it's converging, right? So the PMF of the binomial random variable is converging to Poisson. Okay, so that in many instances when your n is very large, it's more comfortable to work with a Poisson random variable than with the binomial random variable. Okay, so I think I will just talk about continuous random variables, and perhaps we can stop this session. We can have some discussion. Okay, so so discrete now continuous. Okay, so a random variable is said to be continuous if its CDF is continuous. Okay, so CDF should not have any jumps, right? So if its CDF doesn't have any jumps, so then it is said to be continuous, right? So in the case of continuous random variable, you can identify a probability density function. It's more convenient to work with PDFs, right? And these are some properties. But more importantly, let's look at some common continuous random variables. Okay, so the first, the most important one is the uniform, or the most simplest one is like the Bernoulli random variable in the discrete domain. So the uniform random variable is the most simplest continuous random variable. Okay, so this is its PDF and this is the CDF. Okay, so these are the expressions, so PDF and CDF, and then So in networks, you will extensively use the exponential random variable. Okay, so exponential random variable is so it's something of this form. Okay, so its tail is going to decay. Okay, as x increases. So this is fx of x. Okay, and this is its CDF. Okay, so this is a non-negative random variable. Okay. So anyway, there is something known as the memoryless property. So let me not go into that, but I will just want to talk about the standard Gaussian or the normal random variable. Okay, Gaussian random variable, something very useful. You would have come across in a course on communication, or in many areas we use Gaussian random variable. Okay. So this is the very popular known, this is the Gaussian curve, or call it as the bell curve. Okay, and this is the PDF of a Gaussian random variable. Okay, and this is actually the complementary CDF. Okay, this is the this 1 minus the CDF. Okay, and the complementary CDF has this interesting notation known as the Q. It's known as the Q function. Okay. Now if you have another, so this is the notation for the Gaussian random variable. So normal, so this is the mean and the variance. Okay, so the PDF is of this form. So any other random variable, right? So once you know the Q function, so you can compute probabilities for other random variables. Okay, with the different mean and variances. Okay, so for instance, if I want to find out what is the probability that x is greater than some small x, so I can invoke this relationship between the Gaussian and the standard Gaussian random variable. Okay, and then I can express the probability, any desired probability, in the form of Q function. So that way, so even MATLAB has this inbuilt Q function. Okay, so if you have, so you can use this Q function to compute probabilities related to any other Gaussian random variable with different mean and variance other than 0 and 1. Okay. Okay, so let me, I wanted to talk about expectation, which is about the mean of a random variable. Okay, so this for the discrete and this for the continuous. So there is just one part I want to show, and maybe I will stop at that point. Okay, which is about variance. Okay, variance of a random variable. So these are some standard properties of expectation. Okay, for so this table is easy. Okay, so I will just show you the table later and leave at that point. So variance, okay, you may know the variance by formula. Okay, so expectation is like mean of a random variable, right? So what is, on an average, what is the value the random variable takes, or if you conduct the experiment several times and if you take the mean, what is the value it gives. So that's known as the expectation of a random variable. And variance is this. Okay, so this is the variance. Essentially, how much on an average, what is the value the random variable takes around the mean. Okay, how much it varies around the mean. So that's variance. So here is the way to understand the variance. Okay, so I'll use the Gaussian curve only. So here, so what we have is, let's say the blue curve is so mean is 0 in all three cases, and the blue curve is the one where the variance is 1. Okay, so the variance is 1. So that's the standard Gaussian. Now as I start, suppose you decrease the variance. Okay, you start decrease the, so you decrease the variance. Look at the red curve. It starts concentrating. All the probability mass will start concentrating now. It will become lesser and lesser random. Okay, when the variance is less, the random variable is less random. Okay, when the variance is 0, it's essentially a constant. Okay, it doesn't vary around the mean. That means it has to take exactly the value, yeah, near, very close to the mean, right? When the variance is large, it's become more and more uniform type. Okay, your Gaussian distribution, you see it starts becoming more and more uniform, right? So now when you conduct the experiment, you will get values around the mean, well spread around the mean. Okay, so when the variance is large, the randomness is going to increase. Okay, right? So I think, so with that, perhaps I will so end here. Yeah, so this is some this is the table of you'll find it easily. Okay, so distributions, you can have a look at different PMFs, PDFs, their mean and variance and so on. Okay. Okay, so with this I will end this session. So if there are any discussions, yes. Yeah.
Given the PDF, CDF of a discrete random variable,
Ah.
so if the random variable is not taking those values, why it is why should we represent it as a continuous between the, for example, head and tail,
Correct.
between 0 and 1, even though that is not there in the sample space?
Correct.
Why we should put as a,
Right.
does we consider it as a combination of uniform distributions as a discrete random variable? Because
Yeah, so see, the definition of CDF is given. Okay, so in the definition, so there is no restriction on the value of x you can plug in. Okay, it could be any value. Okay, you can put in any value of x. So that's why now we know that in discrete there are only few values it can take, right? So it's more comfortable, that's why, to work with PMF. Okay. Now still we need the definition of CDF, because I only talked about discrete, I only talked about continuous. There are mixed random variables where there can be jump, there could be continuous part. Okay. So in that case there is neither PMF nor PDF. Then you have to talk about CDF only. So if you want to find out certain values, so you need CDF, right? So in discrete case we never use CDF. Okay, we always work with probability mass function. In continuous case we always work with PDFs, probability density function. But these are not the only two types. There could be mixed random variables. Okay, so then you don't have PMF, PDF, right? You need some function that can represent this random variable, right? So CDF is a general thing. Okay, so it exists for any random variable, CDF, right? PMF is only for discrete, PDF is only for continuous, but this is for CDF is for any random variable in general.
like in signals we have decomposition of a signal into maybe set of unit step, linear combination of unit step. Does this have any math that says this kind of CDF can be approximated as set of uniform distributions?
Oh, okay, that's any given CDF combination of uniform. So what can be done is, for mixed random variable, it can be, suppose there is a discrete part and continuous part, so it can be a probabilistic combination of both these parts. So that's there. Now it's like you are asking question like Fourier transform, whether there is something like that. Okay, so not necessarily. I mean, for any signal you can of course find the Fourier transform, find a combination, but in it's not. I mean, I don't find any application, I mean, at least in these scenarios. But mixed random variable, you can find out the discrete part separately. You have a PMF part, you will have a PDF part. You can do the mix of both. So that is possible. With some probability it's going to be this random variable. With some probability it's going to be the continuous random variable. In some cases you can do. Fine then. Huh? Yeah. Thanks.
Thank you so much, sir,
Thank
for
you.
giving wonderful insights into probability theory.
Yeah.